Hello there. In this video we're going to introduce two common types of notation that is often used in advanced level mathematics. The first one is this symbol, for example capital sigma from k is equal to 1 to n of some statement of k, say just k, and also capital pi from k is equal to 1 to n of some expression of k, say just k. We'll define and explain what these representations mean, and also do several examples on how to calculate them. Alright, so this first representation, this little E looking thing, is often referred to as sigma notation, and this capital pi is often called pi notation. Sigma notation is often referred to actually what it represents, and that's summation notation. And sometimes this representation on the right is sometimes referred to as product or not as common productation notation. So important, the prefixes of these words, sum and product, sort of correspond to what these representations mean. So let's do a few examples on how to calculate expressions that are presented in sigma or summation notation. So let's look at the basic. So the sum, k equal 3 to 5 of k. So this is sometimes referred to as the lower limit, in particular 3. 5 is usually referred to as the upper limit, and k is sometimes referred to as the index of the sum. And usually that letter is in the expression to the right hand side. So pretty much what this says is we're going to replace k with all of the numbers from 3 to 5, and we're talking natural numbers here. And then we're going to add them up. So this is going to be equal to, so replace k with 3, that's going to be 3, plus, and then we're going to increment that by 1, so 4, then increment that by 1 to 5. So we have 3 plus 4, which is 7, plus 5, which is equal to 12. Therefore, the sum from k is equal to 3 of 5 of k is equal to 12. Let's do another example. Suppose we have the sum from k is equal to 0 to 2 of k squared. So same thing applies. We're going to replace k with all the numbers from 0 to 2, and then we're going to add up those terms. So this is going to be 0 squared plus 1 squared plus 2 squared. Notice we go from 0 to 2. So this is going to be equal to 0 plus 1 plus 4, which is equal to 5. So another example. Suppose we have the sum from k is equal to 1 to 2 of 1 divided by k. So same thing applies. We're going to replace k with all the numbers from 1 to 2. So this is going to be 1 over 1 plus 1 over 2, which is the same as 1 plus 1 half, which as we know is 3 halves. So another basic example. Suppose we have the sum from k is equal to 0 to 10 of negative 1 to the power of k. So we're going to replace k with all the numbers from 0 to 10. So this is going to be negative 1 to the 0, plus negative 1 to the first, plus negative 1 to the second, plus negative 1 to the third, plus all the way down to, let's go down a few terms, say negative 1 to the 8th, plus negative 1 to the 9th, plus negative 1 to the 10th. So as we know, negative 1 to an even power is going to be 1. So this is going to be 1, and negative 1 to an odd power is going to be negative 1. So 1 plus negative 1 are going to cancel into 0. So the same thing is going to apply here. So 2 and 3 is going to be 1 and negative 1. So those two terms are going to cancel. Notice we're starting with an even and then an odd. Even, then an odd. So 8 and 9 and all the numbers in between are also going to cancel out with each other. And then we're going to just be left with this last term. So this term, or the sum, just reduces to negative 1 to the power of 10, which is equal to 1. So now let's work with a little bit more of a complicated representation. So let's look at a double sum. So the sum from j is equal to 0 to 3 of the sum from k is equal to 4 or k is equal to 0 to 4. And the expression we're going to sum over is j plus k. Some people will not write these parentheses, but I'm just writing them here for clarity. So we're going to be focusing on the internal sum here, and we're not going to really go into details and properties and tricks and shortcuts. We're just going to go about it in a very intuitive way. So we're going to replace k with all the numbers from 0 to 4, and then we're going to add up those expressions. So this is going to be equal to the sum from j is equal to 0 to 3 of, so we're going to have j plus 0 plus j plus 1 plus j plus 2 plus j plus 3 plus j plus 4. Let's simplify this sum in the middle just to make things a little bit clean. So the sum from j is equal to 0 to 4. So we have 1, 2, 3, 4, 5 different j's here. So we have 5j plus 0 plus 1 is 1 plus 2 is 3 plus 3 is 6 plus 4 is 10. Right? Alright, so what can we do? Well, we can replace j with the numbers from 0 to 4 and then add up those expressions. So one way we can do is we can actually distribute the sum because we know sum is commutative over the set of reals. So we can rewrite this instead as the sum from j is equal to 0 to 4 of 5j plus the sum from j is equal to 0 to 4 of 10. And then we can factor out these constants out of the sum since they're all common terms. And then we're just going to have the sum, or 5 times the sum from j is equal to 0 to 4 of j plus 10 times the sum from j is equal to 0 to 4 of 1. Alright, so what is this going to be equal to? So this is going to be equal to 5 times 0 plus 1 plus 2 plus 3 plus 4 plus 10 times 1 plus 1 plus 1 plus 1 plus 1. So notice there's no j term here, so we're adding up 1 5 times. Notice it starts at 0, not 1. So 1 plus 2 plus 3 plus 4 plus 5, different ones. Right? Oh, we started our sum at 4, so let's just replace that with 4. Right? All good, no problem. Alright, so what do we got? So this is going to be 5 times, so 4 plus 3 is 7, plus 2 is 9, plus 1 is 10, plus 10 times 1, so that's going to be 5. So we have 5 times 10 is 50, 5 times 10 is 50, so this is going to come out to 100. It's a beautiful sum. So now let us look at the product notation. So example 6. So this is going to go similarly. So this is going to be the product from k is equal to 1 to 4 of the expression k. So we're going to multiply all the numbers k from k is equal to 1 to 4. So this is going to be 1 times 2 times 3 times 4. So this is going to be 1 times 2 is 2 times 3 is 6 times 4 is this is going to be 24. Alright, so another basic example. Let's consider the product from k is equal to 1 to 4 of 1 over k. So what's this going to be? So this is going to be 1 over 1 times 1 over 2 times 1 over 3 times 1 over 4. And of course this is pretty much the same as the beginning, just the reciprocal. So that's just going to be 1 over 24. Now let's do something a little bit more fun. Let's do the product from k is equal to 2 to 4 of 1 over k plus 1 over k minus 1. So let's replace k with all the numbers from 2 to 4. So this is going to be 1 over 2 plus 1 over 2 minus 1, which is 1, multiplied by 1 over 3 plus 1 over 3 minus 1, which is 2, times 1 over 4 plus 1 over 4 minus 1, which is 3. So we know that 1/2 plus 1 over 1 is going to be 3 over 2. 1/3 plus 1/2 is going to be 5/6. And 1/4 plus 1/3 is going to be 7/12. So we know that 3 times 5 times 7 is going to come out to 105. And 2 times 6 times 12 is going to come out to 144. We notice that the sum of the digits is divisible by 3, so we can divide top and bottom by 3 to simplify. So this is going to reduce down to 35 over 48. All right, so let's just do one more example just to review these concepts. So let's calculate the sum from j is equal to 0 to 3 of the product from k is equal to 0 to 2 of the expression j plus k. So we'll start with this inner product here. So this is going to be equal to the sum from j is equal to 0 to 3 of, so we're going to multiply these expressions and replace k with all the numbers from 0 to 2. So this is going to be j plus 0 times j plus 1 times j plus 2. And what we can do is we can triple expand this expression. So we can do j plus 0 times j plus 1, or just j, since plus 0 doesn't really do anything. So once we expand this expression, one can find that that's going to come out to j to the 4th? No, not j to the 4th. So this is going to be j squared. Let's see, 2j, 3j, so 3j squared, and then plus 2j, right? So then we're going to distribute the sum over each of these just to make this a little bit easier. So this is going to be the sum from j is equal to 0 to 3 of j cubed plus 3 times the sum from j is equal to 0 to 3 of j squared plus 2 times the sum from j is equal to 0 to 3 of just j. Alright, so notice that j is equal to 0 for j cubed, j squared, and j is just 0. So we can actually just simplify this and rewrite this in a more nicer way. So we can just rewrite this as just the sum from j is equal to 1 to 3 of j cubed plus 3 times the sum from j is equal to 1 to 3 of j squared plus 2 times the sum from j is equal to 1 to 3 of just j, right? That makes it a little bit more nicer to write, then we don't have those zeros floating around. So this is going to be 1 cubed plus 2 cubed plus 3 cubed in the first term, plus 3 times 1 squared plus 2 squared plus 3 squared in the second term, plus 2 times 1 plus 2 plus 3 in the third term. So this is going to be equal to 1 plus 8 plus, so 3 times 3 is 9 times 3 is 27, plus 3 times 1 plus 4 plus 9, plus 2 times 1 plus 2 is 3 plus 3 is 6. Right? So we have 27 plus 1 is 28 plus 8 is 36. Plus, let's see, 1 plus 4 is 5 plus 9 is 14. And 14 times 3 is going to come out to 42. And then 2 times 6 is 12. Right? Alright, so what do we have here? So 2 plus 2 is 4 plus 6 is going to add up to 10. 3 plus 4 is 7. Plus 1 is 8, so this is going to come out to 90. So this is just a basic overview of how to use these notations, namely sigma and pi. Sometimes if you see the same sums with lower limit and upper limit, you may just see people just express expressions like this, without actually writing the limits. But that should be a well-defined thing, and it should be stated in whatever literature you're reading. And if you see not a finite number here, but something like the sum from k is equal to 0 to infinity of some expression, this is called an infinite sum, and the same thing can go for a product. We'll discuss these at a later time when we have a couple more details underneath this. Hope you enjoyed.